You guys did a pretty good job of guessing how much I weigh. I'm not gonna tell you. Yet. We're gonna see how you did first. So, I need you to remind me what your guesses were, because I've lost this data. I didn't put it into my calculator like I sometimes do. So can you give me the frequency distribution that you guys had of my, you got it, Jenny? Go ahead.
Yeah, 68 through 76.
By ones? Okay, so 68, 69, 70, 71, 72, 73, 71. Go, beautiful. And the frequencies, my friend?
2, 3, 6, 4, 4, 1, 2, 1, 1.
Oh, not 21. 2,
1, 1.
Yeah, 1. Awesome. Fantastic, fantastic. Good. So I sent you guys home with the one kind of homework you can think about was, are any of those guesses unusual? So we're looking for the outlier definition. So any atypical height guesses, height estimates. What do you say? Any atypical height estimates, and you can't get off by saying, yeah, the 76 is the highest one. That doesn't count. There's no definition of outlier that says the highest data point has to be atypical, or the lowest one for that matter. What do you think? Gesundheit. And there's really only two ways you have to identify them right now. There's a third way I want to hint at today, especially based on what the other class had for guesses. I can't wait to share it with you. But what do you guys say?
76.
76. Why, Skylar?
Well, I graphed it on here.
Excellent, my friend. Let's all do that. Let's do two graphs. Let's do two graphs. Okay, second y equals. We'll do two plots. We'll do a histogram. Okay. So here's a histogram set up, ready to go. And on plot 2, I'll do a modified box. You do modified box plot, right? I'm assuming, Skylar? Yeah. That's the easiest thing to do because it'll automatically do the second outlier identification for you. Oops, that was the wrong button. On. Modify. L1, L2. Okay, so real quick, that's what your plot screen should look like if we're going to run a histogram with a modified box plot together. Now, we still might want to mess with our window a little bit, but at least this will get us, if we do a zoom 9 right now, that'll get us right into both those graphs. So I do a zoom 9. Oops, got to turn the histogram on. There we go. Zoom 9. Okay, I'd like to finagle. I'm going to finagle because it's not.
That's your thing.
Yeah, I know, it's my thing. That's what I do. So your 68 was your lowest guess, and 70, what was the highest? 76? So we'll go 77 by 1. Let's see if that's good enough. Nah, we can do better. We can do better. There we go. That's decent. Maybe it's a little too high.
It's not really a graphic.
Was that Harrison?
Oh, my calculator's just been a little funky.
Oh, okay. If you guys are getting errors, let me know what errors you're getting. In 244 this morning, I had folks that were getting errors, and they didn't let me know until 45 minutes later. And it was something very simple. It was something not related at all to what we were doing in class. And it drove me nuts because they spent 45 minutes trying to get their TI to work and didn't miss the entire conversation we were talking about for 45 minutes, and that broke my heart. So if you ever get an error, just I'd probably fix it really quickly. And chances are, if you have an error, somebody else is getting the same error anyway. So, all right. So Skylar, you took a look at that and said, I got myself an outlier at 76 because of.
Well, on mine there was a little mark.
Yeah.
Hang on.
It's not on yours.
It is not on mine, is there? Here's why. I know I changed this to L2 and it didn't register.
Mine
There we
didn't
go.
register the first time either.
Yeah, it didn't. I didn't hit enter, I guess. Thank you. Let's do this. There's my mark.
Yeah.
Now I'm going to finagle. Thank you, Skylar, for saying that. And Jenny. I'm going to change it again. My apologies. It seems to have it more on. Whoa.
You changed your scale to 4.
Oh God. Why? Because I'm not using the mouse for this thing, I'm used to my thumbs. There we go! So Skylar looks up there and says, oh, this tells me that the largest data point is indeed an outlier. And of the two methods we're talking about, there's the standard deviation method and there's the IQR method. Which one are we using there? Which one are we actually using? We are, Megan, aren't we? Because what's happening with that is, if you didn't make a modified box plot, so if we change this back to an unmodified, which I'm just going to do real quick, check this right, enter, graph. There's your IQR. Stack, boom, that guy right there. That guy right there falls outside of that range right there. Nothing on the low end is too small, but that definitely is too big by that computation. But I like the fact that TIs do it for you automatically. There we go, boom. All right, so awesome, awesome. So yes, 76 is an outlier. 76 inches is an outlier by that method right there. Good, 76 inches, which is 6'4". That's generous. Even with the ponytail, that's generous. All right. How about, anybody do standard deviation? Leslie, did you, anything an outlier by that?
What? I wasn't listening, sorry.
Is anything an outlier by standard deviation? We'd have to figure out the average plus or minus 2 standard deviations. And I think the easiest way to do that is to use the TIs as well, yes? You first, the one thing you have to do, you can't do it graphically. You have to go in and run one of our stats. So we'll do that real quick. You've got to run one bar stats, L1 and L2, just like that. You press enter, okay. You guys guessed on average I'm 71.1 inches. It's actually not damn bad at all. I'm 71.5 inches on average. That's quite nice. I'm just shy of 6 feet. Nice job, nice job. I'm just shy of 6 feet. That's the hair. It's the hair. It makes it look taller than actually. It's the nose too. So I'm just shy of 6 feet. You guys nailed that pretty good. Standard deviation, you guys gave me about 2 inches. So using those 2 values, you can then construct this range of values here. But if I may, like I showed you in a quiz from last week, I'm going to use the variables in the TI to do this rather than actually having to add and subtract things directly, because there's so much rounding that has to happen. So do you remember doing this on the variation quiz? You could go into vars, go to statistics, and there's X bar and S right there. We may have done this in class last week. I don't remember if we did or not, but I know it was on the quiz from last week. So you can go 2, which is X bar, plus 2, oops, statistics is 5, 3. So X bar plus 2S will give you the high end of 2 standard deviations, and then X bar minus will give you the low end. Everybody follow that little button, those little button pushes there? So it's the vars menu. Then you go to statistics, and under statistics you have X bar and S right next to each other. Now if I press enter, this means anybody that guessed over 75.3 inches was an unusually high guess. So that's the high end. I'm going to go one more step here. Anybody that guessed over 75.3 inches, and technically speaking I should really call that 75, because we shouldn't go to tenths of a foot since I told you to round off to the nearest whole inch. But that's okay. And the beautiful thing about doing it this way, is you can just press second enter, and then change the plus sign to a minus sign. And then press enter again. Oops, except press enter and not the plus sign. And this tells me that anybody guessed under 66.9 inches is also an outlier. Technically speaking, that should be 67 inches, I guess. Because it's so close, if we round it off, 67 inches, or 66.9, but nobody did. The lowest guess we had was 68. The lowest guess we had was 68. So there were no outliers here. So the only one outside of here was that 76 inches again is an outlier. There you go. There you go. So these actually agreed this time. They don't always agree. They don't always agree. Sometimes if you run them different ways, you get different levels of agreement. But in this, whoever said I was 76 feet tall, thank you. But that was a little too high.
76 inches.
76 feet. No, I'm friggin' 76 inches high. Thank you for the vote of confidence in my height. However, it's too high to be typical when compared to the rest of the class.
I think it's because I look up at you.
But that's quite all right. Thank you, Jenny. It's quite all right. I think it's the hair. I'm pretty sure it's the hair. Now, the thing is, what are the assumptions that you make for each of these when you do each of these? What assumptions do you make? Can you apply both of these to any data set? Or I should say, take that back. You can apply those to any data set. Should you apply those to any data set? Harrison Chase said no. How come? Why can't you just willy-nilly apply either one of those? Let's back this out a little tiny
So it
bit.
could be like the one on the, you did on this board over here where there's like multiple groups of data.
Well, that's true. That's very true, but that's even more meta than I want to get at.
Oh.
Let me show you what I'm getting at here.
If it's not bell-shaped.
Boom. This one should not be used unless you can arguably say that the data is bell-shaped. That data right there. Okay? And I think a lot of people lean towards not using this one and leaning towards this one. First of all, it's much easier, obviously. All you gotta do is graph it to look. That's fantastic. But number two, there's no restriction on that data at all. There's no restriction on that data at all. You don't have to worry about it having any kind of a shape because it works just based off percentiles. So I think this tends to be pretty popular because of both of those reasons. Because of both of those reasons. And some people look at a shape like this and they're like, I don't know, it's kind of bell-shaped. It's kind of bell-shaped. But a lot of people get a little bit nervous, rightfully so maybe, when you've got a hump like this and then a secondary hump over here. Now, this happened yesterday, just to bring up in the other class, I gotta look at my TI real quick. They had, for their guesses, let me look at it. They guessed between 68, 69, 70, I've erased it, I have to put them in there. I know 68 was the lowest they guessed. They didn't guess as high as you guys. They went up to 75, so that was their highest guess. But these are their frequencies. Let me get in and edit this. They didn't have a 76. And their frequencies on these, this was very, very cool actually. 68, they had 1, 3, 7, 4, 2, 1, 6, 1. And then they didn't have that one because, okay. So this was their results right here. Let me finagle that. There. Let me finagle some more. Okay. That's what they guessed. Which is totally friggin' awesome. Because no matter how you look at this, there are no outliers with these two methods. Now, number one, you shouldn't use this one anyway. You shouldn't use this one because you have, if you ignore this, you've got a bell curve almost perfectly. But that's if you ignore a third of the data set. So you back away and you say, I can't ignore that. So then, you say, I've got that very interesting secondary hump over there. But because the data is so wide and varied, look at your box plot. Your box plot has a crazy wide IQR, which means nothing's going to fall outside of it. But don't you agree that there are some atypical data points? Mm-hmm. I mean, it almost looks to me like you've got, somebody just said, was it Harrison? You said there's two data sets, basically? I think so. I think there's the folks that guess this, and there's the folks that guess this. But the problem is that they're all grouped into one place. And again, I didn't pay attention to who guessed what and where they were sitting in the room and things like that, which would have been fun to kind of analyze. But both of these methods fall short as soon as your data, both of these methods assume that your data is basically unimodal. Both of these assume unimodal data. The problem is, as soon as you get away from unimodality in your data, all kinds of crap happens that you weren't expecting. Like all of a sudden, you shouldn't even be looking at an average of data that looks like this. Because your average is over here somewhere. But that's nowhere near where the modes are, where we go back to the discussion we had in week 2 and week 3 in here. So, I thought about this, and I thought, this might be a good time to talk about a third way outliers are measured. A third way that outliers are measured. And this is probably my favorite way, all in all. The third way to look at the way outliers are measured. And sometimes it syncs up. Sometimes it syncs up with the other two. Sometimes it doesn't. But the third way is any data point that happens less than 5% of the time is considered atypical. Any data point that happens less than 5% of the time is considered atypical. Any data point. So then you have to ask yourself, okay, can we apply that to their data set? And we totally can. We're also going to apply it to yours and see if we get any kind of agreement there. If you apply that rule to their data set, 68, 75, and 73 are all considered unusual because they happen 1 in 25. There's 25, exactly 25 data points in there. 1 in 25 is 4%. So each one of those data points happens 4% of the time, which would fall in under the 5% cutoff. Now I want you to think about that. Why would they use 5% as a cutoff? Where have we heard that before?
2 standard deviations.
2 standard deviations, assuming you have bell-shaped data, captures 95%, 5% on the outside. So if you have bell-shaped data, this one and this one should agree perfectly. They should catch roughly the same amount of things, especially on large data sets. It doesn't always agree with this one, but that's okay. These are constructs. These aren't probability rules that you're going to see today. These are constructs. Okay? But this works great because you don't have to have any specific shape in your data. Any data shape will do. And you can apply that to any data shape whatsoever. Harrison, go ahead.
Doesn't Chevy-Chev's theorem have something to do with that?
It does, but it's so convoluted and general that it's not worth talking about.
Okay.
Yeah, Harrison's mentioning something called Chevy-Chev's, which has to do with any shaped data that you want. And it's beautiful in the respect that it works for any shaped data. It's horribly complex because it gives you such a general, for example, bell-shaped data, at least 68% of your data, or excuse me, 68%, roughly 2/3 of your data is within 1 standard deviation. By Chevy-Chev's, at least 0% of your data is within 1 standard deviation. Thank you! Your height is between 0 and 8 feet. I mean, it's correct, but it's so wide that it doesn't tell you anything specific. I used to teach Chevy-Chev's and I realized it was a losing battle. I don't know if it's the whole USSR thing from 1989, but it's one of those things that it gives you such a generality that it doesn't actually give you anything useful, unfortunately. And plus, with sampling, you're going to see later in the class that we get a bell shape as soon as we start sampling anyway, so we can always use this once we start doing inferential sampling. More on that later. Thank you, yes. Fair? Now, here's what I want to do next. I want to put your results together with the other class's results. Because here's the deal. I look at their results. I look at their graph right here. And it's beautiful. It's beautiful. Oh, pull it down a little bit. It's beautiful. And I'm not saying that that's not bell-shaped data. I'm saying with only 25 occurrences of data, maybe we haven't seen the bell develop itself yet. Maybe if we add more data into it, the shape will fill out. You see what I'm getting at? On small data sets, you're going to get this kind of clumping pretty much on average, which means the variation is going to be wider than it should be. If we combine the data, then I think we might actually get a better picture. Assuming, of course, now we have to understand that when they took the guesses on my height, I was dressed normally. When you took my guesses on my height, I was dressed like an idiot. So it's kind of apples oranges there. It's kind of apples oranges. So there's that to consider. But let's see anyway. I'm going to need Jenny, if you don't mind. I'm going to go stat edit. I'm going to leave theirs in L2. Can you give me your guys' numbers again? I know I have to add 76, and I will do that. Go ahead.
Just the frequencies?
Just the frequencies, yes ma'am.
Yeah, 2, 3, 6, 4, 4, 1, 2, 1, 1.
And I know I've got to come over here, and I've got to add that 76 back in. Which means I have to put a 0 here. Now, I want to show you real quick. You can use your TI as like a spreadsheet in some ways. So what I just did, now one way I could have done that was, as Jenny gave me the numbers, change L2 to be, But I kind of like this idea because I can show you how to use your TI like a spreadsheet. In L4, what I'm going to do is I'm going to put the sum of L2 and L3. So if you used Excel, this is the kind of thing you do. You would type, equals sum this and this and go. So if you ever need to do this, and we'll do it again today. We'll do it again after break when we start collecting data from dice. You put your blinker up on top of L4, and then you just type L2 plus L3. And when you press enter, it sums them all up. And you can do all kinds of cool mathematics with that. Just the only thing you have to remember, make sure that you have your blinker on top of the listing. That's how it's different than Excel. In Excel, you actually put the blinker in the cell, and you drag and you type formulas and do it. In the TI, you have to put it up on top. Make sure we can see that. I think we can. Yeah. So anyway, now what I want to do is I want to look at your results, both classes put together, and see if we see anything that's interesting to us. So I'm going to go back into my plotters. I'm going to adjust my plot 1 so that it's L1, L4. You guys buy that? And same thing with plot 2 because they're tight. L1, L4. Okay? We'll do a little zoom. Actually, I can probably hit graph. No, I probably can't. If I change that to 77, I can though. Let's see if that works. Oh! Nope, not quite, not quite. Hang on. Window, let's bump it up because I have more frequencies now. Let's go to 20. All right. So we definitely still have this hump over here, which is interesting. But look at the box. The box shrunk in a little bit, didn't it? That's because we added 2 data sets together, and most of those data were towards the center of that. It's still a little wider than it should be because of that secondary hump that's over here. So it still has the same kind of shape that the first classes did, but this guy over here definitely got larger because that's where most of your guys' guesses were. This got a little bit taller too, because some of you guys did guess out there. At least 1 or 2 guesses from this class were in that spike. But you see how it's starting to flesh out a little bit more. Interesting. But nothing showing as outliers. Nothing showing as outliers based off your quartile range. And I would still be hesitant. I would still be hesitant to check it versus calling it a bell curve, because it's not quite showing me yet. It's actually showing me, if anything, it's showing me that I've got maybe more of a secondary curve than I did before. We can try the 5%. We can try the 5% rule. Real quick, I don't know how many data points there actually are. I'm going to run 1 bar stats real quick on L1 and L4. There are 49 altogether. So if I go back to my graph and I trace it, let me come over to here. Only 2 people voted me 73 inches. So 2 out of 49 is roughly 4 out of 50, isn't it? Which is roughly 8 out of 100. So that's about 5%. That wouldn't fall in here. But this 76 still kind of looks like an outlier, doesn't it? That's 1 in 49. That's about 2%, right? That's about 2%. So even though it's not registering as an outlier using this, that 76 would register as an outlier because it was the only one in 50 that was that high, which falls under the 5% cutoff. So you see how sometimes they don't agree with each other perfectly? That's okay. These are people-made things. They don't have to agree perfectly. They don't have to agree perfectly. It's just that sometimes they do, depending on certain assumptions. Go ahead, Michael.
Isn't 2 out of 50 4%?
Oh, of course it is. It's 4%. Thanks. I'm doing 2 out of 100 in my head. But still, it comes under 5%. It's not quite as impressively as 2. But it comes in under the 5% cutoff.
The other one, there was 2 in 49.
2 in 49 would be 4%. Oh my God, it's 4 in 50. 1 in, yes, thank you, 4%. I'm sorry, I can't do math in my head right now. 4%, and you got your 2% over here. So actually, technically, these guys, now the problem with that, the problem when you start getting close to 5%, and we're having this discussion in my 244 class right now, a data set that's still this small, if you will, it's still small. If I collate more and more of it in there, we begin to see, I've never been called 76 inches tall before. I'm convinced that one is unusual. But I do get called 73 inches and 74 inches quite regularly. This is not that unusual. So as we see more and more data points pop in, you're going to see those percentages rise. I doubt very much this one will, though. And that's what I'm kind of getting at. That's why more data, as long as it's collected well, is always better than more data that's collected poorly or less data that's collected well. Is that fair? Good. No, it's not fair. No. Yes, it's okay, it is. Thank you, Michael, for the arithmetic help. Much appreciated. Fair enough? So here's 3 ways to mark outliers. They're not the only ways, but they're the ones that are used most. Especially this one. This one we use in 244 pretty much all the time. All the time. So what I want to do now is I want to put this to work with what I just gave you guys as far as dice go. So let's do a little experiment or collect some new data. I think we're done with the height data.
How are you?
Where's the dice at?
So, just under 6 feet. So do a 5'11" and a half. I said that right. 5'11" and a half, just under 6 feet.
Nice, huh?
Or 6'4". I'll let 6 feet go with that.
Yeah.
So, here's what I want you guys to do. Take a few moments right now. Roll 1 die. We'll use 2 dice maybe by the end of class. Take one of your dice. Take one of your dice, roll it 10 times, and make a note of what you get each time. Okay?